Okay, in today's lecture, we're going to cover the section 1.4 material on the matrix equation A times X is equal to B. So we'll discuss that equation in full detail in this section. And the idea that we're going to be looking at in this section is to try to describe a linear combination of vectors. So a linear combination like we saw in the previous section, 1.3, will be viewed as the product of a matrix and a vector. Or as we'll see towards the end of this section, we can express systems of linear equations as the product of a matrix times a vector. So to do this, let's start by introducing a little bit of terminology. So we'll start with the following definition. So here, if A is an M by N matrix, M rows by N columns, and the columns of this matrix are given by the vectors A1, A2, up through AN. So these vectors are the columns of our matrix A. And if X is some vector in Rn, so a column vector, for instance, with N rows and one column, then we would define the product of the matrix A and the vector X, denoted as A times X, as the linear combination of the columns of A using the entries of X as the weights of that linear combination. So let's see exactly what we mean by this. So the product of a matrix A times a vector X, where A is the matrix that has the vectors A1, A2, up through AN as its columns, and X is some vector in Rn, so its entries we might call X1, X2, up through Xn, is defined as the following. So it is a linear combination of the columns of A, so some sum of constant multiples of the columns of A, where the entries of X are the weights of this linear combination. So the first entry of our vector X, X1, is the weight of the vector A1. So we have X1 times A1, plus, for the next part of our linear combination, we have a weight of X2 for the vector A2, so X2 times A2, and then we keep taking the sum of these products down through the last term in our vector. X sub n is the weight for the vector A sub n. So this linear combination of the columns of A with weights given by the entries of X is how we define the product of A and X. Now, one thing to note here is that the product of a matrix and a vector cannot be defined for any matrix and any vector. So one subtle thing in our definition here, the matrix A that we're considering is an M by N matrix. So it has N columns, and the vector X that we're considering must be a vector in Rn. That is, the length of our vector X, or the number of entries of X, has to be the same as the number of columns of A. So here we can only define A times X if the number of columns of A is equal to the number of entries in our vector X. Okay. So now that we know how to multiply a matrix by a vector, let's look at some examples. So in this first example, we are told to use this definition of A times X to compute the following products, and if a product would be undefined, we need to explain why. So let's look at part A. In part A, we have a matrix A, which is a 3 by 1 matrix, or we could consider it as a column vector, times some vector X, which is a 2 by 1 column vector. So the question is, first, does this product exist? So notice that the number of columns of A which would be one column, is not equal to the number of entries of x. We had 2 entries in x. So in order for this product to be defined, these inner dimensions, when I write out my product, must be the same. In this example, these are not the same value. So this matrix times this given vector is not defined. So for part A, we could write that this product is undefined since the number of columns of our matrix A is not equal to the number of entries of the vector x. All right, so in part A, we had a product which was undefined. We've stated our reason why. So in part B, let's look at another one. In part B, we have the matrix A, which is a 2 by 3 matrix, 2 rows, 3 columns, and we're multiplying by a column vector x, which is a 3 by 1 column vector. So we see here that the number of columns of A is equal to the number of entries in x. So here, since these are the same value, our product will be defined. Now let's think about how this product is defined. Using the definition that we saw above, this product is defined as a linear combination of the columns of A with the weights given by the entries of x. So our first entry of the vector x is 1, and that is the weight for the first column of A, which is the vector 8, 5. Then we add, for our next weight, we take the second entry of the vector x, which is 2, times the second column of A, which was the vector 3, 1. And then we add the third entry of x, which was a negative 3, times the third column of A, which was negative 4, 2. And so let's now simplify this expression using the vector operations that we saw in section 1.3. So the first thing I could do is distribute each of these scalars, 1, 2, and negative 3, through to each vector. So 1 times 8, 5 is simply 8, 5. Plus, if we distribute 2 times the vector 3, 1, we have 6, 2. And then if we distribute the negative 3, let's distribute the negative to make this a plus. So our negative 3 times negative 4 gives us a positive 12. And then our negative 3 times 2 is a negative 6, or adding negative 6 there. And then taking the sum of these 3 vectors, well, to add vectors, we add component-wise. So for our first component, we have 8 plus 6 plus 12. So 14 plus 12, or 26. And for our second component, we have 5 plus 2, which is 7, minus 6, leaves us with a 1. So this vector is the product of our matrix with this vector. Now, one thing to notice here that we'll talk about in more detail in chapter 2 is the size of the vector that is returned. So here we were multiplying a 2 by 3 matrix A by a 3 by 1 vector x. So we saw as long as those inner dimensions were the same, 3 and 3 in this case, then our product is defined. Now, what size did we get for our product? Well, we had a 2 by 1 vector as our product. So to get the size of this product, we're going to look at the outer entries. So here the size of our product will be a 2 by 1. So the number of rows is the same as the number of rows of A, and the number of columns is the same as the number of columns of X. And here, since we're working with X as a vector, we always have just one column in this case. All right. So let's look at some applications of this product of a matrix with a vector. So in these next examples, we're going to make use of the definition of A times X to transform a matrix equation into a vector equation or vice versa. So in our first example here, we want to rewrite this matrix equation. So here we are multiplying a matrix A, which is a 4 by 2 matrix, by some vector X, which is a 2 by 1 matrix. So the product will be defined. So a little review here. For A, we had a 4 by 2. For X, we have a 2 by 1. So since these inner dimensions are the same, we can define our product, and the size of our product will be determined by these outer dimensions. So as the size of this product, we will get a 4 by 1 column vector, which is shown here. So let's rewrite this equation as an equation just involving vectors instead of matrices. So in order to multiply A times X, well, we take the first element of the vector X, which was -2, as the weight of the first column of A. Now the first column of A is 7, 2, 9, -3. And then we add the second element of X, which is -5, times the second column of our matrix A, which is -3, 1, -6, 2. And this is equal to the vector on our right-hand side, which is 1, -9, 12, -4. And you can see if you were to simplify this expression on the left-hand side, you do indeed get this column vector on our right-hand side. So this equation now only involves vectors, so this is the vector equation that we wanted. It no longer involves matrices, but vectors. So in our next example, we've got a similar problem, but working in the opposite direction. So here we are given a vector equation, that is some equation involving vectors. So here we're taking a linear combination of 4 vectors with weights given by x1, x2, x3, and x4, and the linear combination is equal to some vector 4, 13. So we want to rewrite this vector equation as a matrix equation. So here we're taking a linear combination of 4 vectors, and each of these vectors is 2 by 1. So we're taking the linear combination of those 4 vectors where the weights are given by x1, x2, x3, and x4. So the length of our vector x is going to be 4. So we're going to be looking at a matrix A that has 4 columns, and the columns are given by these vectors within our linear combination. So let's take those 4 vectors and make them the columns of a matrix. So for our first column, we're going to have 4, -2. For our second column, we have -4, 5. For the third column, -5, 4. And for our fourth column, the vector 3, 0. So this is our matrix A, which is a 2 by 4 matrix. And we're multiplying this by the vector x, whose weights are the weights shown in this linear combination, x1, x2, x3, and x4. So this is a vector x, which is a 4x1 vector. So taking the product of a 2x4 matrix with a 4x1 vector, we should get back a 2x1 vector, which is the vector given on our right-hand side of the equation for 13. So this equation that we were given involving vectors has now been rewritten in terms of a matrix times a vector, which is known as a matrix equation. So let's look at some other examples. In this next example, we're going to illustrate that a linear system can be written in terms of either a vector or a matrix equation, and then start relating some concepts that we've seen from our earlier sections to matrix equations. So here we're given the following linear system. We have 3 equations involving 2 variables, x1 and x2. And we are told to write this system first as a vector equation and then as a matrix equation. So an easy way to first write this as a vector equation is to try to think about the left-hand sides of each of these 3 equations in terms of vectors. So notice that this left-hand side of our equation, we could think about this as being the sum of 2 vectors with weights given by our variables, x1 or x2. So from each of these equations, if I were to think about having a weight, x1, I would multiply the weight by the vector of coefficients for this x1 variable. Now in my first equation, the coefficient of x1 is equal to 8. For my second equation, the coefficient of x1 is 5, and for my third equation, the coefficient of x1 is 1. And then I am going to add another vector, or constant multiple of a vector, where the weight of that vector, use red here, is the variable x2. So if I factor out an x2 from each of these equations, then I'm multiplying by the vector whose entries are the coefficients of x2 in each equation. So for my first equation, we had a coefficient of x2 as -1. For the second equation, we had 4x2, and for our third equation, -3x2. And then this is equal to a 3x1 column vector, where my entries are the constants on our right-hand side, 4, 1, and 2. And you can see, of course, if you were to distribute these weights, x1 and x2, to each vector and take the sum, you would get exactly the expression on the right-hand side of these 3 equations. So what we have here first is our vector equation. And then we are supposed to also write this as a matrix equation. So to write this as a matrix equation, we can use the definition of A times X. So for our matrix A, we take the vectors within our linear combination. So the first column of A will be the column vector, 8, 5, 1. And the second column of our matrix A will be the second column vector, -1, 4, -3. And then we're multiplying by the vector x, whose weights were, or whose entries were the weights in this linear combination, namely x1 and x2. And this is equal to the vector on our right-hand side, which was 4, 1, 2. So this is our matrix equation. So here we have a matrix A times some vector x, where x is our vector of unknown variables, in this case x1 and x2. And this is equal to some column vector B, where the elements of this B vector are the constants on our right-hand side. So notice that A is the coefficient matrix for our system. B is the vector of constants on the right-hand side of our equation. So we've already been writing systems in terms of augmented matrices, where the augmented matrix is formed by combining the matrix A with the column vector B. So as this example illustrates, we can write linear systems as either vector equations or as matrix equations. And if we're writing it as a matrix equation, we have something of the form A times X is equal to B. So when we study linear systems throughout this course, we will sometimes rewrite them as matrix equations, particularly when we get into our chapter 2 material. We'll see why that's so useful. So this fact that we can express a linear system as either a vector equation or a matrix equation leads to the following result. So it says if A is some m by n matrix whose columns are the vectors a1 through an, and B is some vector in Rm, so that is an m by 1 column vector, then the matrix equation A times X equals to B would be equivalent to or have the same solution set as the vector equation x1 times a1 plus x2 times a2 up through xn times an is equal to b, which in turn would be equivalent to or have the same solution set as the system of linear equations whose augmented matrix would be the matrix formed by taking the columns of A, A1, A2 up through AN, and augmenting with the vector B of constants on the right-hand side of our equation. Now, since these vectors in our augmented matrix, A1, A2 up through AN, were the columns of a matrix A, for simplicity, this augmented matrix will sometimes be denoted as capital A with a boldface or vector B. So rather than writing out each column of A with B, we could write just the matrix capital A augmented with that vector B. All right. So let's use that theorem to consider when a matrix equation, or consider finding the solution of some matrix equation, making use of what we know about linear systems. So for the given matrix A, a 3 by 3 matrix, and a column vector B, some 3 by 1 column vector, we want to find the augmented matrix for the linear system corresponding to the matrix equation A times X equals to B, and then solve that system and write the solution as a vector. So we're trying to solve the matrix equation A times X is equal to B for the unknown vector X. So we know what A and B are. The question is, what vector X would we be multiplying A by in order to have our output equal this vector B? Now, our previous theorem said that this matrix equation is equivalent to the system of linear equations, which is expressed by the augmented matrix AB. So let's consider the augmented matrix A, B. So taking this augmented matrix, we have, our first column of A was 1, -3, 0. Second column of A was 2, -1, 5. And our third column of A is 1, 2, 3. And then we are augmenting with the vector B, which was the column vector 0, 1, -1. Now recall in your textbook, they would not use that vertical bar notation through the matrix. They would just write this as a 3 by 4 matrix. but my personal preference is to always include that vertical bar that separates my matrix A from the vector B, so that I know where the equal sign lies throughout this system of equations. So this is the augmented matrix for the linear system. That's the first part of the question. Then we are told to solve this system and write our solution as a vector. So recall one way that we can solve linear systems, probably the most efficient way that we'll see, is to row reduce this matrix down to row echelon form or reduced row echelon form. So looking at this matrix, well, we have a 1 in as the lead entry for our first row. And then I know that I want to kill off the entries below this, make them 0. So my lead entry, or my first entry in the third row is already 0, so I need to kill off this factor of -3 in my second row. And an easy way to do this would be to take row 2 and add to it 3 times row 1. So my first row remains the same. I have 1, 2, 1, 0. And my second row becomes, let's see, we have 3 minus 3 is 0. I've got 6 minus 1 would be 5. 3 plus 2 is 5. And then 0 plus 1 would give me 0. And for now, I'm going to leave my third row alone. 0, 5, 3, -1. So my first column is exactly what I want for reduced row echelon form. I've got a 1 for the leading entry in my first row, and zeros everywhere above and below it. So moving to the leading entry in my second row, well, I have a constant of 5, and I know I want to try to kill off the entries above and below that value. So looking below this value of 5, well, I have the leading entry in my third row is also 5. So I could simplify there pretty easily by taking my third row and subtracting the second row from it. So for right now, I'm going to leave my first row alone. I've got a 1, 2, 1, and 0. Now, if I perform this row operation, let's see what we have for our third row. So I have 0 minus 0 is 0. 5 minus 5 is 0. And 3 minus 5 leaves me a -2. And performing that same operation on the right-hand side of our equations, I've got a -1 minus 1, which leaves me -2. Now for that second row, I'm also going to perform another operation. I know that I want this lead coefficient in my second row to be a 1. And here, not every entry in that second row is a multiple of 5, so we're going to have to introduce some fractions here. But to get that 1 entry in the lead coefficient, or the lead entry for that second row, I could simply divide the second row through by 5. So in this same step, I'm also going to take 1/5 of my second row, which will make the second row 0, 1, 1, 1/5. So now let's see what we can do. In my first row, I have a lead entry of 1 with zeros above and below it, a lead entry of 1 in my second row, and I've got a 0 below it, but I need to kill off the +2 that appears above it. In my third row, I have a lead coefficient of -2. I know that I want to have a 1 there, and I see that my right-hand side is also -2. So an easy way to solve for, or to get a 1 for that third lead coefficient in the third row would be to simply divide that third row through by -2, or take -1/2 of the third row. So that would make my third row 0, 0, 1, 1. Sorry, it's a little cramped here. My second row, I'm going to leave alone for right now. I've got 0, 1, 1, 1/5. And I'm going to try to kill off this 2 in the second column of my first row using this pivot position of 1 in the second row's second column. So here, to kill off that entry of 2, I could take my first row minus twice the second row, which would give me 1 minus 0, 2 minus 2 is 0, 1 minus 2 is negative 1, and then 0 minus 2 times 1/5 gives me a negative 2/5 here. So let's see if I can smash that in here. We've got a negative 2/5 on that right-hand side. So now my first 2 columns are exactly what I want. I've got a 1 on these diagonal entries, or my pivot positions, with zeros above and below. And in my third row, I've got that 1 as my leading entry, but I need to kill off the negative 1 and the positive 1 that appear above it to get this into reduced row echelon form. So in my last step here, to simplify my first row, I'm going to take row 1 and add row 3 to it, which gives me 1, 0, 0. And on the right-hand side, we had a negative 2/5. I'm adding 1, which leaves me 3/5. For my second row, to kill off that 1 in the last column, I'm going to take row 2 and subtract row 3 from it, which would leave me 0, 1, 0, and 1/5 minus 1 gives me a negative 4/5. And my last row was 0, 0, 1, 1. So I now have this in reduced row echelon form, and I can read off my solution directly. Recall that these entries in our augmented matrix are the coefficients for these unknown variables, x1, x2, x3, and in general some constant b. So our first row of this augmented matrix says that 1x1 is equal to 3/5. Our second row says 1x2 is equal to negative 4/5. And our third row says that 1 times x3 is equal to 1. So we've got our solution, but in the problem statement, we were told to write our solution as a vector. So the vector x that we're looking for here is the vector whose first component, x1, is 3/5. The second component, x2, is negative 4/5, and our third component is 1. So what we found here is the vector x such that if we multiply the given vector A by this, or the given matrix A, by this vector x that we just found, we will get as our product the given vector B. So because of that theorem that we had just seen, since a matrix equation has the same solution set as the linear system whose augmented matrix would be AB, then by considering that augmented matrix and solving the corresponding system, we get a solution of our matrix equation. Okay, so let's look at the last part of this section on the existence of solutions. So what we have established is that a matrix equation, something of the form AX equals to B, has the same solution set as the vector equation given by the linear combinations of the columns of A with weights given by the entries of X. So this matrix equation, in other words, has a solution if and only if the vector B can be written as a linear combination of the columns of A. So let's consider the question of whether a solution would exist for a given matrix equation. So in this next example, we are given a matrix A, a 2 by 2 matrix, and a vector B, some 2 by 1 column vector whose elements are unknown, B1 and B2. And for this problem, we're supposed to show that the matrix equation, AX equals B, does not have a solution for some choices of this vector B. And then describe the set of all vectors B for which the matrix equation AX equals B does have a solution. So we know that the solution set for this matrix equation would be equivalent to the solution set for the linear system that would have an augmented matrix given by AB. So as with our last example, let us consider the augmented matrix AB, or as I would write it, A with the vertical bar separating the vector B. So we're looking at the following matrix. The matrix A was -3, -4, 9, 12, and we are augmenting with our vector B, whose elements were B1 and B2. So let's see if we can solve the linear system described by this matrix. So here, in order to start moving this towards row echelon form, I know that I need to get rid of the 9 in this bottom left entry. And an easy way to do that would be to take row 2 and add to it 3 times row 1. So I'm going to use the -3 in that first pivot to eliminate the 9 below it. So for now, let me leave my first row alone. I've got -3, -4, B1. And when I perform this operation, let's see what we have. So I would have a -9 plus 9 is 0, -12 plus 12 is 0, and then 3B1 plus B2 for the entry on that right-hand side. So what we see is that our second row in this echelon form is a row of all zeros. And the only way that this system will be consistent is if 0, which is the entry on our left-hand side of the equation, is equal to 0. If this expression on the right-hand side, 3B1 plus B2, is anything other than 0, we have an inconsistent system, as we saw from our theorem in section 1.2. So in order for this system to be consistent, we have to have that right-hand side of our equation in the second row equal to 0. So here, let's say the following. The system is consistent if and only if the value of 3B1 plus B2 is equal to 0. So in other words, if that equation is not true, then we don't have a solution. So certainly there are some choices of this vector B for which this matrix equation AX equals to B does not have a solution. Now, we are asked also to describe the set of all vectors B for which AX equals B does have a solution. So as our description, we could say, well, algebraically, the elements of B have to satisfy 3B1 plus B2 equals to 0. So let's think about what that sort of equation describes. So this is a linear equation involving two variables, B1 and B2. Equivalently, we could think about this condition as being B2 is equal to -3 times B1. So this is defining a line in the plane, in R2, a line of slope -3 passing through the origin. So here we can say this equation defines a line in the real plane. All right. So we're looking at, for the set of all B for which AX equals to B has a solution, we might say something like this. Our solution set is the set of vectors B. So here we're looking at a set, not a specific vector, such that the first component, B1, is a free variable, and B2 has to equal -3 times B1, such that B1 could be any real number. So this defines a line in the real plane, line here of slope -3, y-intercept 0, so passing through the origin. All right. So let's look at another example similar to this, but with maybe a larger dimensional matrix or vector. So here we are given a matrix A, which is 3 by 3, and a vector B, which is 3 by 1. And the problem is the same here. We're supposed to show that this equation, AX equals to B, does not have a solution for certain choices of B, and then describe the set of all vectors B for which AX equals to B does have a solution. All right, so let's see what we have here. In order to see whether our matrix equation has a solution, we would consider the system of linear equations corresponding to the augmented matrix A with B. So for that matrix, we have our first row is 1, -3, -4, B1. For our second row, we have -3, 2, 6, B2. And for our third row, we have 5, -1, -8, and B3. So to solve this, we want to try to put this matrix in reduced row echelon form, or at least echelon form. So here we start with a pivot of 1 in this first column, and we need to kill off the -3 and the 5 that appear in the rows below that. So to get rid of the -3 in our second row, we can take row 2 and add 3 times row 1. So my first row will remain 1, -3, -4, B1. When I perform this operation to my second row, I get 3 minus 3 is 0. -9 plus 2 is -7. -12 plus 6 is -6. And I've got 3B1 plus B2 for the right-hand side. Now in this same step, I'm going to kill off the 5 in my lead entry of the third row by taking row 3 and subtracting 5 times row 1, which makes my third row, let's see, we've got a -5 plus 5 is 0, 15 minus 1 is 14, we've got 20 minus 8 is 12, and in our right-hand side, we have -5B1 plus B3, or equivalently B3 minus 5 times B1. So I have now a first column of 1, 0, 0. When I move to the lead entry in my second row, I've got a -7, and I see that I could kill off the entry of 14 that appears below that pretty easily by using the -7 in that pivot position. So I could do that by taking my third row and adding to it twice the second row. So my first row remains 1, -3, -4, B1. My second row I'm going to leave as 0, -7, -6, 3B1 plus B2. And when I perform this operation on the third row, let's see what we have. We've got 0 plus 0, a -14 plus 14 is 0, -12 plus 12 is 0. And let's see what we're left with. So combining the B1 terms, I'm taking my second row times 2, so I would have 6b1 minus 5b1 leaves me b1. Combining the b2 terms, well, I'm multiplying the second row by 2, so I have 2b2 with nothing from the third row involving b2, so plus 2b2. And then combining the only b3 term, well, 2 times the second row has 0 b3 plus my 1 b3 leaves me with b3. So again, we see that in echelon form, not reduced row echelon form here, our last entry, our last row is a row of all zeros, and the only way that this system is consistent is if the constant on the right-hand side is also equal to 0. So here we could say that this is consistent if and only if the sum of b1 plus 2b2 plus b3 is 0. All right. So here we can think about this equation involving, so it's a linear equation in 3 unknowns, b1, b2, and b3. So a linear equation in 3 variables, we could say this defines a plane in space, that is in R3. So our solution set, or the set of all vectors b such that ax equals to b would have a solution, is some plane in space. So the point that we're making in these last 2 examples is the following. For a matrix equation, ax equals to b, it may not be consistent for all choices of b, because the echelon form of this matrix A could have a row of zeros. So a matrix equation may not always have a solution, depending on the form of the matrix A. So the question that we will ask at the end of this section is, when would that matrix equation have a solution for every choice of B? So to answer that question, we need a little terminology. So we would say here that a set of vectors, v1, v2, up through vp in Rm, so those are column vectors of length m, is said to span all of Rm if every vector in Rm can be written as a linear combination of v1 up through vp. Or equivalently, if the span of those vectors, v1 up through vp, is equal to all of Rm. So the question is, well, when would a set of vectors span all of Rm? And the following theorem gives us an answer to that question. So let's say that we have a matrix A, which is an m by n matrix. Then the following 4 statements are all equivalent. So any 2 of these statements of the 4 below are equivalent to each other. So in part A, for every vector B in Rm, the the matrix equation A times x equals to B has a solution. So if a matrix equation has a solution for every vector B, that is equivalent to, for any vector B, we could express that vector as a linear combination of the columns of A, because we saw that that matrix equation can be written as a vector equation where we have a linear combination of the columns of A. Equivalently, part C, we would say that the columns of A span all of Rm. So if we can write any vector B in Rm as a linear combination of the columns of A, we say the columns of A span all of Rm. And the last condition here, which is the condition that we will use most frequently to check whether a set of vectors spans all of Rm, is the following. does the matrix A have a pivot position in every row? All right. So given that these four things are equivalent, let's make use of this theorem to answer some questions about the span of a set of vectors. So in this next example, we are given a matrix A, a 4x4 matrix, and the question is whether the columns of this matrix A span all of R4. And why or why not, we have to justify our answer here. So the way that we will typically check this is by using this condition D in our theorem. Does the matrix A, whose columns are a given set of vectors, have a pivot position in every single row? So to answer that, we need to try to put this matrix in echelon form. So looking at our matrix, well, we already have a 1 as the leading entry of our first row. So we need to kill off the positive 1 and the negative 2 in our third and fourth rows. So to do that, with my first row operation on A, in the third row, I'm going to take row 3 and subtract row 1 from it. So my first row remains the same, 1, 3, negative 2, 2. My second row remains the same, 0, 1, 1, negative 5. And when we perform this operation in the third row, I have 0, negative 1, negative 1, and 7 minus 2 is positive 5. And to kill off the negative 2 in that fourth row, I'm going to take row 4 and subtract. I could take twice row 1 or twice row 3. I'm going to stick with row 1. So let's see what this leaves me with. So I would have 2 minus 2 is 0. 6 minus 6 minus 8 is negative 14. Positive 4 plus 2 is 6. And a negative 4 minus 1 would be negative 5. So now we can see pretty quickly here that our second row and our third row are equivalent. One is just the negative of the other. So to simplify this towards row echelon form, I could take row 3 and add row 2 to it. And my first row will remain the same, 1, 3, negative 2, 2. My second row will remain 0, 1, 1, negative 5. And when I add the second row to the third, I get a row of all zeros. And my last row I'm going to leave alone. So here, in order to put this thing in echelon form, well, I know that my row of zeros needs to be the last row, or in other words, I need every non-zero row to appear above a row of all zeros. So I want to change my third and fourth rows. So to interchange these, row 3 and row 4, we have 1, 3, negative 2, 2, 0, 1, 1, negative 5, 0, negative 14, 6, and negative 5, and then a row of all zeros. In order to move this just one step closer to row echelon form, or to put this in row echelon form, well, I have 1s for these lead coefficients. Below those 1s, I need to have all zeros, so let me kill off the negative 14 in my third row by taking the following. So I'm going to take row 3 plus 14 times row 2. So my first row is still 1, 3, negative 2, 2. Second row is still 0, 1, 1, negative 5. And for my third row, I will have 0, 14 minus 14 is 0, 14 plus 6 is 20, 14 times negative 5 is what? Negative 70 minus 5, so negative 75, and then a row of all zeros. So this matrix I have put into row echelon form, not reduced row echelon form, but we can see here that since we have a row of all zeros as our last row, we do not have a pivot position in every single row. So since this fourth condition, condition D in our theorem, does not hold, we know that the columns of A cannot span all of Rn. So for our answer here, we would say no, the columns of A do not span all of R4. And the reason is since the rows, or since, let's say this, since the last row of A has no pivot position. So making use of our theorem, we see that because a condition D does not hold, none of A through C can hold. Therefore, condition C is not met, which says that the columns of A would span all of Rn. So if any one condition does not hold, that means none of the other conditions could hold since they are all equivalent. All right. So in our last example, we are given a set of vectors, v1, v2, and v3, which are vectors in R4. They have length 4. And the question is, does the set of these vectors, v1, v2, and v3, span all of R4? And then why or why not? So in order to answer that question, well, we could think about making those vectors the columns of a matrix A. So looking back at our previous theorem, we know that a set of vectors would span all of Rm if the columns, which are those vectors of some matrix A, span of all of Rm. And then once we have it in matrix form, we could row reduce it to see if condition D is met. That is, does that matrix A have a pivot position in every row? So let's look at this. Looking at a matrix A that has these vectors as its columns, we have 1, 0, negative 1, 0, 0, negative 1, 0, 1, and 1, 0, 0, negative 1. So to row reduce this matrix, well, in our first row we have a lead entry of 1, and I need to kill off the negative 1 that appears in my third row. So to do that, I'm going to take row 3 and add row 1 to it, which gives me 1, 0, 1, 0, negative 1, 0, 0, 0, 1, and in my last row I've got 0, let's see, so it looks like my pen is going out on me here. Let's see if it'll hang in there for just a little bit. I have to write by hand at the end. So our last row, we have 0, 1, negative 1 for that last row. So now it's a little closer to echelon form. In this second row, we have a lead coefficient of negative 1. I need to kill off the positive 1 that appears below that. So I can do that by adding row 2 to my fourth row. So this is equivalent to taking row 4 and adding row 2 excuse my handwriting, I'm having to use my hand here. So our first row is 1, 0, 1. And then in my second row, I know that I want that leading entry to be a positive 1 instead of a negative 1. So I could get that by taking the negative of my second row. So taking the negative of row 2, we have 0, 1, 0. My third row I'm going to leave alone. I've got 0, 0, 1. And when I added row 2 to row 4, I have 0, 1, negative 1. So in my last step, I've killed off one of these ones here. I have as my last row 0, 0, negative 1. So now, to simplify a bit further, in this lead coefficient for my third row, I have a positive 1. I need to kill off the positive 1 that appears above that and the negative 1 that appears below it. So in my last step, I will see if I can perform those operations. So here this would be equivalent to the system that we get by taking my first row or my third row and adding the fourth row to it. So that would be taking row 1 plus row 4, or by taking row 1 row 3 plus row 4. So this leaves us with 1, 0, 0, 0, 1, 0, 0, 0, 1, and a row of all zeros. So we see again in this example that we have a row of all zeros as our last row. Therefore, it does not have a pivot position. Therefore, these 3 vectors cannot span all of R4. In order for those rows to span R4, this matrix would have to have a pivot position in every row according to our previous theorem. So we could then ask ourselves, what we see in this last example is that we have a set of 3 vectors of length 4. So when we put these columns in, or these column vectors into a matrix, we have a 4 by 3 matrix. That is 4 rows, but only 3 columns. So is it possible for a set of 3 vectors of any 3 vectors to span all of R4? Well, we would need a pivot position in each of the 4 rows, but we only have 3 columns. Therefore, it is impossible for a set of 3 vectors to span all of R4, and we could pose that question more generally then. If we had a set of, say, n vectors, and we asked, could it span Rm, where m is a larger number than n? Would it be possible for those vectors to span all of that space? So by using a similar argument to what we've considered here, we could say no. In order to span an m-dimensional space, you would need at least m vectors to accomplish that. So that finishes up the section 1.4 material on matrix equations. And in our next section, we'll start to consider some solution sets of linear systems by using a matrix equation and look at some different forms that we might have for a certain type of solution or a certain type of system known as a homogeneous